Okay. Good morning, good afternoon, whatever time of day it is for you. I am not going to give you clues on these guys. I can't even spell today. There we go. Of course, I will give you clues if you see me in person or, online. You know what I mean. Okay, but we're going to start in on what we need to know to do number 3 and 4. And number 5, I'm just going to give you a little clue. It's about center of mass. Okay, question 3 on the worksheet is the discrete question. And question 4 on the worksheet is the calculus version of the same question. All right, so hopefully I will not mislead you about which question I'm working on. I'll just call it, hey, discrete center of mass question. Okay, so first I want to say something about this specific exercise. Okay, whenever you have some kind of symmetric shape, it could be a rectangle or a circle, not a triangle, but something is symmetric in the right way, then you can find the center of mass by just taking the whole weight of the whole mass of the whole object. And if it's really obvious where the center of mass is, then you can assume that the entire object is one point source right there. Okay, and in this particular exercise, it's about a clock that Dr. Robinson made, and the clock the clock has a pendulum, and the pendulum from top to bottom has a length of 117 millimeters, so it's a little more than a meter. Okay. And then what happens is, so wherever the center is, so it's 1117 over 2, and that's where you're assuming the center of the mass of this stick is. It's a long skinny stick. There's a picture of it in the diagram. Now this is a little bob that he puts on to help control the speed of the clock. And so in this question he has the pendulum bob, not at the bottom here, but like somewhere on the stick because it's supported on the stick. So that's why when you read the question, it says it's at a distance of like 1037. So again, if we're here at the top is 0, and then maybe here is going to be 1073 instead of 37, whatever. Okay, so this is going to be where the actual center is. So the bob is centered where the distance is, where the location is, but the rod, the center of mass for the rod is half of the length of the rod. Okay, so that's sort of background information. Okay, so hopefully you can visualize this, but I find it easier to just draw it horizontally, whatever is going on. If you have on your x-axis, there's a 0, and you have a couple of different point masses. You have, mass 1, mass 2, mass 3, and the 0 can move around. It actually doesn't matter where you put it. You put it wherever it's convenient, and it magically doesn't actually matter. But just for the sake of argument, I'm going to put all my masses to the right of the 0, and I'm going to say that this here is going to be distance 1, and this guy is going to be distance 2, and this guy is going to be here, distance 3. Hopefully you can see that. All right, so if you took physics, this force times distance equals work, and if you made this the fulcrum, all this would work. This whole thing would make sense. So that it really is the same physical problem, but we give it different words. We say mass times distance equals moment of inertia. Okay, so you can think of placing kids on a seesaw. Some people call that a teeter-totter, a seesaw, teeter-totter. I don't know what you call this toy. It's this toy where you put a kid on either side and they go up and down and up and down, and if the kid on the top jumps off, the other way around. If the kid at the bottom jumps off, the kid at the top falls. You know, you don't want that to happen. Okay, that kind of toy. Okay. So what you want to do is you want to replace all these point sources with a single point source. And what you do is you replace it with a mass where mass 1 plus mass 2 plus mass 3 is at a certain distance. Let's call it distance 4. Okay, so you call this mass 4. So you want to find, you want to solve for this. Mass 1, distance 1, plus mass 2, distance 2, plus however many of them you have, it doesn't matter how many you have, is equal to mass 4 times distance 4, and the only thing you don't know is the distance 4. This is the only unknown. Okay? So you have all the information now to solve problem 3. It actually does not require any calculus. No calc on question 3. None whatsoever. No calculus. Okay, so question 4 is like question 3, but now we add calculus, and I'm not going to do the exact same problem that's in the worksheet, but I'm just going to make up some other bogus question. All right, I'm going to have a rod with a density function. This is a delta. Okay, so density, I'm going to make my density x squared, and I'm going to make the rod a whole whopping 2 meters long, or 2 inches, or whatever it is. I don't actually care. 2 units long. It could be 2 miles for all I care. And so what I want to do is I want mass times distance. Okay? So what does that mean? The mass is the delta function, and the distance itself, I'm going to just do the easiest thing possible. I'm going to say 0 is 0, and the distance is x. So wherever the mass is, and then the x is the distance from 0. So it's just, this is really literally the dumbest thing I could do. All right? And so I'm going to just integrate that from 0 to 2. So in this case, I have x times x squared, and that's from 0 to 2, and that's going to be x cubed. So when I integrate that, it's x to the 4th over 4 from 0 to 2, and in this case it's going to be 16 over 4, which is going to give me 4 grand total. And so this is all the moments, sum up all the moments. And this is what happened in the discrete case when we did m1 d1 plus m2 d2, etc. When we did that. And then we want to see that's equal to m4, and I'm just going to call it m total, distance total. And so wait, we are looking now, we need to find where the center of mass is, which is d total. So that means we need to actually calculate this mass too. So we just calculated the stuff on the left-hand side and found out it was 4. But now we have to calculate the total mass. And it's like, well, it sounds like it's going to be a pain. Well, sure it is. But I'll make the problem pretty easy for you. And so this is just going to be x squared from 0 to 2, dx, and blah, blah, blah. And then you're going to end up with 8 over 3, let's just say. Okay, so this is the actual mass total. All right, so that's summing up all the masses. So how do you find that distance? Well, what did we do before? So we wanted to do all the moments divided by all the masses is equal to the resulting center of mass, which are the overall center of mass. Okay, so how do you do that? Well, what's all the moments? All the moments looks like this. X times, or delta x times x, you can put them in either order, and from 0 to whatever the length of your rod is. Let's make this look more generalizable. And then all the mass is going to be exactly the same thing, which makes it infuriating because if you have problems with anything remotely like dyslexia, this is just going to make your eyes bug out. And so this is the formula for center of mass. There we go. Okay, so do you want a hint for the last one? No, you don't. Then you can just stop the video. You don't need to watch it. So this problem is just think about a long rod, and this is just kind of worded in a bit of a hazy way because it's a thinking question. So it wants you to think about what if somewhere on this end of the rod it's very heavy for some reason. You can think of a violin bow, or you can think of a fencing tool, like some kind of a weapon. There's a lot of things, a conductor's rod, if they're doing like a musical conductor, but there's a lot of things you'll run into that are constructed in everyday life where it's heavy at one end, but it's not heavy all the way through. So the point is, can you construct one of these objects that's super heavy here, but outside of this heavy zone, like somewhere over here, is where the center of mass is? How would you construct something like that? Can you construct something like that? And just play around with it. You can do the discrete or continuous version of this problem. So you could just make up an f of x and like see what makes that work. Or you can just put little point masses to see. Just play with it. It's just a play with question. And it derives from the self-same clock that Robinson was making when he wrote these questions. Well, he made the clock before, but anyway, you can see a picture of that clock that he made. It's in the worksheet, and if you want to know more about the clock, I'll be happy to tell you about it and point you to some more videos. It's rather clever, I think. Anyway, I will see you all soon. Bye-bye.